In this video, we're going to look about logarithms, and at the end of it, you'll be able to understand what are logarithms, rules governing logarithms, special cases in logarithms, and the different examples of solving logarithmic problems. Without wastage of time, let's jump into the video. What is a logarithm? A logarithm is a quantity that represents a power or an exponent to which a fixed number called a base must be raised to produce a certain number called an argument. In theory, 10 squared or 10 to the power 2 equals to 100. And from index to logarithm notation, log of 100 to base 10 equals to 2. From definition, a logarithm is this quantity that represents this power or an exponent to which a fixed number called a base must be raised to produce a certain number called an argument. It's a quantity that represents this power to which this number called a base must be raised to produce this number called an argument. That's a logarithm. Let's look at the rules governing logarithms. Rule number 1, the product rule. Suppose you have log of a base x plus log of b base x. This should equal to log of the product of the arguments ab to base x. For example, log of 2 base 10 plus log of 3 base 10 should equal to log of 2 times 3 base 10, which equals to log of 6 to base 10. Rule number 2, the quotient rule. Suppose you are given log of a base x minus log of b base x. This should equal to the log of a by b base x. For example, log of 18 minus log of 9 should equal to log of 18 divided by 9, which equals to the log of 2. Rule number 3, the power rule. Suppose you're given log of m raised to a power of x to base n. The power should become the coefficient of this logarithm, and this becomes x log of m base n. For example, log of 3 raised to a power of 2 to base 2. The power, which is 2, should become the coefficient of this logarithm, and this becomes 2 log of 3 base 2. Rule number 4, the ident rule. The ident rule states that if the argument is the same as the base, or the argument equals to the base, then the whole logarithm should equal to a 1. In theory, log of a base a equals to 1. Log of 5 base 5 equals to a 1. Log of infinity base infinity should equal to a 1. For example, log of 100 base 10. This equals to, remember 100 is the same as 10 squared. Log of 10 squared base 10. From power rule, 2 becomes the coefficient of this logarithm, and this becomes 2 log of 10 base 10. But from identity rule, log of 10 base 10 equals to 1. This implies that we have 2 times 1, which equals to a 2. Therefore, log of 100 to base 10 equals to a 2. Rule number 5, change of base formula rule. This rule allows us to change a base of a given logarithm to any other base. For example, suppose we have log of a base b. If we introduce a new base of x, this will become log of a base x divided by log of b base x. For example, log of 4 base 3. If we want to introduce a new base of 2, using change of base formula rule, this will become log of 4 base 2 divided by log of 3 base 2. But 4 is the same as 2 squared, so this will become log of 2 squared to base 2 divided by log of 3 base 2. From power rule, 2 will become a coefficient of this numerator. So this will become 2 log of 2 base 2 divided by log of 3 base 2. From identity rule, log of 2 base 2 equals to 1. So we will have 2 into 1 divided by log of 3 base 2, which is the same as 2 divided by log of 3 base 2. Rule number 6, logarithm to index notation. This will simply help us to convert a logarithm form to an index form. Suppose you have log of a base b equals to x. This from logarithm to index notation is the same as b to power x equals to a. For example, log of 25 base 5 equals to 25 is the same as 5 squared log of 5 squared to base 5. From power rule, 2 becomes the coefficient of this logarithm, and this will become 2 log of 5 base 5. And from identity law, log of 5 base 5 equals to 1. This will equal to 2 into 1, which equals to 2. This implies that log of 25 base 5 equals to a 2. And this from logarithm to index notation will become 5 to power 2 equals to 25, which makes sense mathematically. Special cases in logarithm. The first special case is the zero rule. The zero rule states that log of 1 to any base equals to a 0. Suppose we have log of 1 base b. This should equal to 0 in accordance with the zero rule. In detail, if we have log of 1 base b, from indices, any number raised to a power of 0 equals to a 1. This implies that instead of a 1, let's have log of b to power 0, but to base b. And from power rule, 0 will become a coefficient of this logarithm, and we will have 0 log of b base b. And from identity rule, log of b base b equals a 1. This implies that we have 0 into 1. But 0 times 1 equals to a 0. Therefore, log of 1 to any base equals to a 0. The second special case is the reciprocal rule. Suppose we have log of 1 out of a base a. This should equal to negative 1. In detail, if we have log of 1 out of a base a, from indices 1 out of a is the same as a to power negative 1. This implies that we will have log of a to power negative 1 base a. But from power rule, negative 1 should become a coefficient of this logarithm. So we will have negative log of a base a. And from identity rule, log of a base a is the same as 1. So we will have negative 1 into 1. But negative 1 times 1 equals to negative 1. For example, if you are given log of a half to base 2, from indices, a half is the same as 2 to power negative 1. This implies that we will have log of 2 to power negative 1 base 2. And from power rule, negative 1 will become a coefficient of this logarithm. So we will have negative log of 2 base 2. And from identity rule, log of 2 base 2 equals to 1. So we will have negative 1 into 1. And negative 1 times a 1 equals to a negative 1. Also, if we have log of 1 out of x base c, from indices 1 out of x is the same as x to power negative 1. So we will have log of x to power negative 1 base c. But from power rule, negative 1 will become a coefficient of this logarithm. So we will have negative log of x base c. The third special case is the use of change of base formula rule to swap the base with the argument of a logarithm. Suppose you're given log of a base b. On swapping the argument with the base, this should equal to 1 divided by log of b base a. In detail, given log of a base b, if we want to swap the base with the argument, we should introduce a new base, and this base should be equal or the same as the argument. And in this instance, we should introduce a new base of a. So we will have log of a base a divided by a log of b base a. And from identity rule, log of a base a should equal to a 1. So we'll have a 1 divided by log of b base a. Thus swapping the base with the argument. For example, if we have log of 2 base 16. In accordance with the third special case, we should introduce a new base and it should be a base of 2. So we will have log of 2 base 2 divided by log of 16 base 2. And from identity rule, log of 2 base 2 equals to 1 divided by 16 is the same as 2 to power 4. This implies that we have log of 2 to power 4 base 2. And this will equal to 1 divided by, from power rule, 4 becomes the coefficient of the denominator. So we will have 4 log of 2 base 2. And from identity rule, log of 2 base 2 equals to 1. So we will have 1 out of 4. Therefore, log of 2 base 16 equals to a quarter. Example 1. Find the value of x in log of x plus log of 5 equals to 2. Given log of x plus log of 5 equals to 2. But what are the respective bases of these logarithm terms? Suppose you're given log of 2 without any base. By default, this is the same as log of 2 to base 10. Even if you're given log of x without any base, by default, this is the same as log of x to base 10. So this implies that you have log of x to base 10 plus log of 5 to base 10 equals to a 2. And from product rule, we will have log of x times 5, which is the same as log of 5x. So we will have log of 5x to base 10 equals to a 2. And from logarithm to index notation, we will have 10 squared equals to 5x. But 10 squared is the same as 100. We will have 100 equals to 5x. Dividing 5 on either side, we will have 5 divided by 5. We'll have 20 equals to x. But before we conclude, let's first test for whether the value of x equals to 20 satisfies the equation from the problem. So when x equals to 20, from the problem, we have log of x to base 10 plus log of 5 to base 10 equals to a 2. But our x equals to 20, so we will have log of 20 to base 10 plus log of 5 to base 10 equals to a 2. And from product rule, we will have 20 times 5, which is the same as 100. So we will have log of 100 to base 10 equals to a 2. But 100 is the same as 10 squared. So we will have log of 10 squared to base 10 equals to a 2. And from power rule 2 will become a coefficient of this logarithm. So we will have 2 log of 10 to base 10 equals to a 2. And from identity rule, log of 10 to base 10 is the same as 1. So we'll have 2 into 1 equals to a 2, which is the same as 2 equals to a 2. But since the left hand side equals to the right hand side, therefore our value of x indeed equals to a 20. Example number 2, log of x plus 6 to base 3 equals to 2 plus log of x minus 2 to base 3. Find x. So we are given log of x plus 6 to base 3 equals to 2 plus log of x minus 2 to base 3. And we are required to find the value of x. On collecting the like terms, we will have log of x plus 6 to base 3 minus log of x minus 2 to base 3 equals to 2. And from quotient rule, we will have log of x plus 6 divided by x minus 2 but to base 3 equals to 2. And from logarithm to index notation, we will have 3 raised to a power of 2 equals to x plus 6 divided by x minus 2. But 3 squared is the same as 9. So we will have 9 equals to x plus 6 divided by x minus 2. On cross multiplication, we will have 9 into x minus 2 equals to x plus 6. This is the same as 9x minus 18 equals to x plus 6. And on collecting like terms, we will have 9x minus x equals to 6 plus 18. This is the same as 8x equals to 24. dividing by 8 on either sides, we will have our x equals to 3. 24 divided by 8. This is the same as 3. But before you conclude this, first test for whether our value of x equals to 3 satisfies the equation from the problem. So for x equals to 3, what do we have? Let's substitute for x in this equation. So we will have log of 3 plus 6 to base 3 equals to 2 plus log of 3 minus 2 to base 3. And 3 plus 6, that's a 9. So we will have log of 9 to base 3 equals to 2 plus log of 1 to base 3. But 9 is the same as 3 squared. So we will have log of 3 squared to base 3 equals to 2 plus log of 1 to base 3. And from power rule, 2 will become a coefficient of this logarithm. So we will have 2 log of 3 base 3 equals to 2 plus log of 1 to base 3. But from identity rule, log of 3 base 3 equals to a 1. So we will have 2 into 1 equals to 2 plus log of 1 to base 3. So we will have 2 equals to 2 plus, and from 0 rule, log of 1 to base 3 or log of 1 to any base equals to a 0. So we will have a 0 here. Therefore, we have 2 equals to a 2. And since the left hand side equals to the right hand side, therefore our value of x indeed equals to a 3. To support us, don't forget to subscribe to Outek Math, and for more examples, check out the links in the description. Otherwise, see you in the next.